Okay, so in this video, we're going to be talking about deriving the wave equation. So we're done with the heat equation. Now we're going to be talking a bit about the wave equation, which many of you might already be very familiar with if you've taken physics classes. All right, so how this goes is that we're going to consider a string. And we're going to be thinking about how it might be vibrating. So we're thinking about waves on a string. So just to give you a visual picture to have in your mind, you can think of a string maybe like this that's attached here, and if it was perfectly still, it would be lying along this line. And just like in the heat equation, we're going to be considering an infinitesimally small sliver of the string. So we're going to consider a portion of the string from some spot x to x plus delta. So let's maybe say that this guy here is x. Let me actually make this a different color so it's more visible what's going on here. So let's say this guy is x, and here we have x plus delta. And before we go any further, I want to make clear the assumptions that we make. So we're going to make the following assumptions, which are definitely false, but approximately true. Okay, so first of all, we're going to assume that each little spot of the string, so not literally, but if we kind of think of the string maybe as made up of little pieces, little atoms, then we want to make the assumption that each little piece has motion only in the vertical direction. So I'm saying that this is, it's not quite true, because if we look at this picture of the string that I've drawn here, it is hopefully evident that if we were to measure the length of the solid string, that's just a bit longer than the length of the string if it were still, if it were here, going directly from one node to the other node. So because the string, when it's moving outside of its resting position, is a bit longer than it would otherwise be, there's some stretching going on in the horizontal direction, but we're going to assume that that's negligible. Okay, and the second assumption we're going to make, which is similar, is that the angle the string makes with the horizontal at any point is also negligible. So what I mean by that is if we look at, say, this point here, and we look at this tangent line to the string here, and we measure the angle that this makes with the horizontal theta, we're going to make the assumption that this is very close to zero, this theta. Okay, so to do the derivation of this equation, we're going to start with Newton's law. This is our, in this wave equation situation, the version of, or our analog to the conservation of energy principle that started us off with the heat equation. So Newton's law says that force equals mass times acceleration. And we're going to now plug in F, M, and A. So F is the most complicated guy. Now kind of looks a bit like conservation of energy. So we want to think about the total vertical. So we're again just considering things in the vertical direction. We're thinking now about the total vertical force, F, on our segment from x to x plus delta. And this is, so first of all, we have, we're going to account for some arbitrary external force, Q. But we're going to multiply this by rho naught delta, and when I explain what all these letters are, it will be clear why we're doing this. So this Q is the kind of analog to what we also called Q in the heat equation. So it's just where we put all the forces that are just kind of there being done to the string, not something that's intrinsically part of the properties of the string. Okay, so in this equation, rho naught is the mass density of the string. And it's maybe not ideal this differs from the heat equation, but in the heat equation the mass density was about mass per volume. But here, since the string is generally thinner than this rod that we were studying before, we're kind of thinking of it as being infinitesimally thin. So this mass density now is mass per, not volume, but just length. So I want to make that very clear that this is a different, if we were thinking in terms of units, this would have very different units. So it would have something like kilograms per meter units. Okay, now Q is some external force. The most common one might be gravity. We're thinking about an honest to goodness string. And this is per mass. So just like gravity has the same units as acceleration, here we're thinking about Q as being some force per mass. Okay, so now let's think about what's going on here. So we have this force per mass Q, and then we're multiplying it by the total mass of our little segment, which is the mass density per length times the length delta. Okay, so hopefully that makes sense. And then we also have to account for the kind of internal workings of this, situation of a string vibrating. So the internal workings are due to the tension that's happening in the string. So the tension is, let me choose green. So the tension here is, let me choose actually different spots for x and x plus delta, because these ones will not make things so clear. So let's choose this spot for x and this spot for x plus delta. Okay, this will make things more clear. So the tension in the string is a force that is tangent to the graph of the string. Right, so it's a force, a vector that is pointing in the tangent direction of the string at these points. So here we're going to call this guy, let me make this bigger actually. We're going to call this guy here t of x. Maybe I'll also give it time. And remember, this is a vector valued function. You can write it like that to be really clear. Let me also make this guy a bit longer. So this is t of x plus delta, little t for time. Okay. And now we're only thinking about things in the vertical direction. So we want to pick out the vertical, like maybe what you would normally call the y component of these vectors, txt and tx plus delta t. So we want to pick out, let's see, this vector here. That is the y component of this green vector txt. Okay, so we can do that mathematically by thinking about this horizontal and the angle that the string makes with the the tangent line to the string makes with the horizontal there. And we're going to call this theta xt. And similarly here, we're going to call this guy theta x plus delta comma t. Okay, so these are the kind of internal forces acting on our segment of the string. So we're going to add them in to Newton's equation. So we have our guy here, tx plus delta t, and now here I'm treating this, I mean, maybe we should really think of it as a vector valued function, but here, as I'm writing it without a little hat like this, I'm thinking of it really just as the magnitude of the force. So to get the, from the total magnitude of the force, to get the vertical magnitude of the force, we're going to pick that out by multiplying this by sine of theta at that spot, x plus delta. So this is the force being pulled, or this is the force that with which the string is being pulled on its right hand end to the right. And then there's also the force being pulled on its left hand end to the left. So of course that guy will have a negative sign attached to it, because again txt is just the magnitude, and we're looking at sine of theta at that position xt. So to be clear, T of xt is the tension on the string at xt. And let's say, to be even more clear, the magnitude of the tension. So maybe you want to think about it as a vector, but here we're thinking about it really just as the magnitude. And theta is the angle that the vector t, which is to say, well, either this vector of tension or the tangent vector to the string, makes with the horizontal. Okay, so now putting these terms into the f part of Newton's law, we get the following. So we're going to get rho naught delta q plus t of x plus delta t sine theta x plus delta t minus t xt sine theta xt. And now this is going to equal m times a. So the mass of our little segment is this mass density times the length. And the acceleration we're going to write in terms of the vertical. Now I'm going to stick with the notation that the book uses, which is not to use maybe what you would expect for the vertical, something like y. We're going to use u instead of y. So u is the measuring the vertical displacement. So the acceleration is the second time derivative of u. So where u is the vertical displacement, where you might otherwise use the letter y instead of u. Okay, now from this equation, we can divide everything through by delta. And now we're going to see some things that look familiar to us. So these terms here don't have any delta factor in them, so we're going to put these guys over delta, of course, equals rho naught, partial squared u, partial t squared. As delta goes to 0, and we take the limit, this becomes, so we still have rho naught q, that doesn't change. This guy becomes the derivative of this expression, capital T, xt, sine theta, xt, with respect to position. So we have t, xt, sine of theta, xt, and again, this term, of course, doesn't change since it doesn't have a delta in it. Okay, I'm going to give this equation a name, star, so we can use it in the future. Okay, now let's look at this and use assumption 2. So we didn't use assumption 1. Let me just take a second to explain this. We didn't use assumption 1 very explicitly anywhere, but assumption 1 makes it possible to think of just a little sliver, our guy from x to x plus delta, kind of just moving up and down, and the fact that this sliver doesn't get any bigger or smaller makes this whole logic even possible. And now assumption 2 we're going to use very explicitly. So if we look at, if we think about what partial u partial x is, which is something that hasn't appeared yet, this is tan theta. So let's think maybe about a little picture here. So let's think maybe about a little string like this. And suppose that we're interested in this spot here. Now, what is du d theta? Well, du d theta is the slope of this tangent line here. So we can think of this if we kind of use a bit of hand waviness here to think about this guy as a fraction. We can think of du over dx to be composed of a little guy du, which is the vertical component of the slope, and a little guy dx, which is the x component of the slope. And if we think about the angle that this tangent vector makes, well, that tangent vector wouldn't be the slope, would it? Maybe a tangent vector like this makes with the horizontal, which is to say this little angle theta here. We can see that the ratio of the magnitude of du over the magnitude of dx is just tan theta, right? Because tan theta is opposite over adjacent. Okay, so now tan theta, of course, we can also write as sine theta over cosine theta. And now assumption 2 is going to kick in, and we're going to find that this is basically sine theta, because we're assuming that theta is, not equal to 0, but basically 0. And when theta is basically 0, cosine theta is basically 1. Okay, so now we're going to plug this in to our almost there heat equation. So we see that our equation becomes rho naught q plus partial x txt of du dx, and still over here we have the same stuff. Okay, so we're basically done. I think I said heat equation a second ago. I meant wave equation. This is the wave equation that we wanted to derive. But now we're going to just see that it looks a bit nicer if we make some extra assumptions. So we will often assume that t is constant. And I think in physical terms, you might call that, if t is constant, the string is what you would say perfectly elastic. So it's some property of the string that makes t constant, and it's fairly common. But we're not in a physics class here, so we're going to kind of ignore that and just say often we assume t is constant. And when t is constant, we can, of course, bring that guy out of the partial derivative. We see a lot of rho naughts everywhere, so we can divide, things by rho naught. And just put a u here. And we find this guy on the other side. So this is the heat equation when t is just a constant. And also we will assume not all the time, but often, that q equals 0. So this becomes, if we just make q 0, we see this. Well, maybe I won't actually box this one. And when we have all these assumptions so that this wave equation is so nice, we often write it in the following form. Okay, and I just want to make some comments that often what's happening when we assume that q is 0 is that we're again making some approximating assumptions, not really that q is 0, but that the force is basically negligible. And when that's the case, we often can first calculate an equilibrium position of the string. Say when we have gravity acting on a literal string, we can calculate an equilibrium position of the string. And then from there, we can measure the displacement relative to the string, then assuming that q is 0. Okay, so see the book for that. There's a little bit of explanation at the end of the section, and there's a homework question about this. Okay, so that's it for today for this video. If you guys have any questions that you maybe would normally ask in class, I really encourage you to ask them on Piazza. That's the perfect place.